Greetings. In this one, I'll be talking about the possibility to break out the velocity vector into its individual components. I'll be talking in 2D about the projectile. Let's say I'm launching this kind of projectile under the angle of 30 degrees. So let's say I'm launching a ball and I throw the ball. Let's say it starts here, and the initial, of course, the velocity vector of it will be this. The velocity vector of it will be, let's say, we'll have this direction of this arrow, so it needed to make this angle alpha or whatever, let's say theta as well. Regardless of how I call the angle, it will be 30 degrees to be exact. So this velocity vector that the ball is moving at will make this angle of 30 degrees with the x-axis. Let's say this is the horizontal x-axis, this is the vertical y-axis. But regardless of all of that, the direction is this, and its magnitude, that means the speed at which the particle is moving in the direction of this arrow, will be, let's say, 10 meters per second in the basic units. And what I'm trying to, let's say, determine is there's actually two components hidden behind this vector. Of course, this vector is in its own direction, but it can be also expressed as the sum of these two vectors. This vector and this vector. So let's say this is the vertical component of it, and this is the v sub h horizontal component of it. And what I mean by this is when one has such a vector, it's quite easy to break it down into two parts it is made up of, kind of. Because this is the velocity by itself, this direction. But it can be broken out into the horizontal component and into the vertical one. When it is like this with the axis, it's very nice to see. So basically, when it moves horizontally, that's the horizontal component of it. So the projection, the shadow right below the axis, right below this arrow, when light is shining from the top straight down, then this shade, this shadow right below it is the VH, the horizontal component of this vector. And to complete, to add these two means to complete the equivalent expression to just this vector by itself. And to that, so I will be adding this vertical component VV, and that is the vertical part. This is the vertical part, which again is like if it's the same magnitude as one will be shining from this side and the shadow projected below this onto the y-axis. So it's the length that this arrow reaches on the y scale, that's the vertical component, and the extent to which this arrow reaches on the x scale is the horizontal component. So these two components right below the arrow of its own direction and also along it on the y direction, these are the two components I can break it down into. And now I can also view it from the perspective that really this is my initial, that's my default vector, and so I can break it down into these two sides of a perpendicular triangle. So I have these two, first parameter and the second parameter. What it means that either I'm talking about this vector of the velocity, or I'm talking about these two added together. Because when I take this one, this vector by itself, it just goes to the right. And then this is a separate vector, I add its tail to the tip of this previous one, then it will reach to the same point. So either this one, this straight one, or this one with the straight turn towards the left, they will both reach to the same point. But these two, they only talk about just the x direction and just the y direction. This one talks about in a mixed fashion, graphically showing exactly the straight movement from this point to this point. In either case, either the addition of these two or just this one by itself finally add up to the same result. And so if this one has a magnitude of 10 meters per second, I can, using trigonometry, calculate the magnitude of these two. And I can do it in this following way. That if I know this angle between the x-axis, in this case, that's probably the most common case. I know this angle between the x-axis and the direction of the velocity vector, then I can calculate both the horizontal component and the vertical component. As you see, v sub h, I mean by the horizontal component, and the vertical component is v sub v. And how am I going to calculate it? Is basically by using sine and cosine. So, for example, this side over this side, it means the vertical component over the actual original vector. This over this, opposite over hypotenuse is sine of the angle made right here. And the angle right here in this case is 30 degrees. So 30 degrees right here. That tells me that the vertical component will be this angle's sine, so in this case sine of 30 degrees, times the original vector. So the only thing I need to do is take this magnitude and multiply by sine 30 degrees to get this value, this magnitude, the magnitude of this vector. If I want to get this vector's magnitude, then what I do is, again, I will, in this case, apply cosine. So I know this side over this side is the cosine of this angle in between them, because there is a perpendicular angle right here, and the right angle triangle properties with trigonometry apply right here, of course. So V sub h over the actual initial V by itself will correspond to cosine of whatever the angle between these two sides is. In this case, again, 30 degrees. And so I can multiply both sides by V, and I get the expression for the horizontal factor of this original vector, which will be just the vector original one times cosine 30 degrees to get the horizontal value. Alright? So that gives me the understanding that I can either say, well, there's this vector with magnitude 10 meters per second, or there is this vector with 10 meters per second times cosine of 30 degrees, or this one, and then plus this one, which is again 10 times cosine of, times sine of 30 degrees. So just to give a concrete example, let's say I'm still using and taking these same values, but my example in this case might be, let's say, for example, there's this ball thrown, and its velocity right here, the angle it makes with the x-axis or with the horizontal ground is 30 degrees, and its magnitude again is 10 meters per second. All right, and what I want to find is, let's say I wanna determine in how long will it fly over this place, which is horizontally displaced, let's say 20 meters. So here it is 0 meters from the beginning, and along this way, along this ground, this is 20 meters horizontally displaced. And I want to know, this ball is moving 10 meters per second in this direction, but it's moving at a slightly smaller speed, or a slightly smaller magnitude velocity in just the horizontal direction. So I want to determine in how much time it will be flying over this point. It won't be just 2 seconds, because this is 20 meters, this is 10 meters per second, because the direction is in here, so the horizontal component will be slightly smaller. I want to know how long it will take for it to finally fly over this point. And to determine that, I will use cosine. So I know that the horizontal component is the reflection of this vector right on the horizontal ground. And to get the horizontal component, the rule is take the angle it makes with this vector I'm given. So that is 30 degrees. Take the cosine of it and multiply the initial vector by it. Because I know that this is like, let's say, the vertical component, and this is the horizontal component, just completely the right angle triangle with the ground and with the initial vector. I know that VH by geometry over V is equal to cosine of 30 degrees. Alright? And that gives me straight away the horizontal component. So I'm just trying to figure out how quickly it is moving just in this direction, in the horizontal direction, not in this direction that we were given. We were given 10 meters per second in this direction, but it's actually moving at a different speed in this direction. So that's what I'm going to figure out now. So the horizontal velocity therefore will be from this equation, where I know that this over this is equal to cosine of 30 degrees by trigonometry. Well, that will be this vector times cosine of 30 degrees. And what that is basically just to substitute, well, this is 10 meters per second, and I'm multiplying by cosine of 30 degrees. Cosine of 30 degrees is square root of 3 over 2. It's a table value, that's why I actually in the first place chose this 30 degrees. Just multiplying things out, what it really gives is this rather quite a nice expression, 5 times the square root of 3 meters per second. Alright? So I got this expression right here, and what it tells me is that although the particle or the ball is moving at 10 meters per second in this direction, towards this point that I'm actually caring about, it is moving in this at this speed, which is a little bit smaller. It's a little bit smaller than 10 meters per second. And how to calculate until when it will reach the 20 meters? Well, there's this equation saying the velocity equals distance over time, alright? And what I can do right now is basically express time from this equation. So I can multiply both sides by t, vt equals s, and then I want to express t, so that is s over v. And I know that the velocity I'm caring about is just the horizontal one. I cannot use the 10 meters per second, but it's this direction. I'm only caring about this direction. So this direction is the 5 times square root of 3 that I calculated. This is a number by itself, right? And so what I'm going to be doing is, of course, 20 meters, but it travels in over the time of 5 times square root of 3. So it's going to take meters per second. Right? These are just the units that I put into the parentheses. So the time that is elapsed until I reach about this point of 20 meters away horizontally from the origin is 4 over the square root of 3. Alright, I can divide both this and this, the numerator and denominator, by 5. So I get 4 over square root of 3 seconds.